Hello everyone. So my name is Jovancio and my partner is Christania Putri R. And today in this video we will present about our machine learning project and assignment, which is we are going to discuss about percentage of forest area by each country, and this imply with the SDGs point number 13.
Forest ecosystems play a crucial role in maintaining environmental balance, supporting biodiversity, and regulating climate. However, many countries are experiencing changes in forest coverage due to factors such as urbanization, deforestation, and environmental policies. Understanding these trends is important for sustainable development and environmental planning. With the availability of historical environmental data, machine learning techniques can be applied to analyze patterns and predict future forest coverage. By combining predictive modeling and clustering, it is possible not only to estimate further trends, but also to group countries based on similar characteristics.
Despite the availability of global forest data, there are several challenges. First, it is difficult to accurately predict future forest coverage trends for each country. Second, countries exhibit different patterns of forest changes, making it hard to categorize them effectively. Third, there is a lack of simple tools that allow users to analyze, compare, and interpret forest data interactively. Therefore, a system is needed to first predict future forest coverage using historical data, to identify patterns among countries through clustering, provide an interactive way for users to explore insights.
The dataset used in this project contains historical data on forest area percentages for multiple countries over several years. The data represents the portion of land area covered by forests measured annually. The dataset was obtained from the World Bank Open Data Platform, which provides reliable and publicly accessible global indicators. The features contains country name, country code, year or time series, and forest area by the percentages of land area. The data characteristic is first one, time series data spanning multiple years. Second one is some missing values handled through data cleaning and converted into long format for analysis.
The main objective of this project is to analyze and understand global forest coverage trends using machine learning techniques. Specifically, the project aims to 1. Predict future forest area percentage for each country using regression. Second, identify patterns and similarities among countries using clustering. Third, categorize countries into meaningful groups such as improving, stable, or critical. Fourth, evaluate model performance using metrics such as mean squared error or MSE and k-fold validation. The last one is to provide an interactive system that allows users to explore predictions and insights.
Next is methodology. First, we use linear regression or prediction. Linear regression is used to model and predict forest coverage over time for each country. The input will be the year, the output will be the forest area by its percentage. The model linears the relationship between time and forest coverage, producing a trend represented by the slope. Why we choose the linear regression? The first one is because forest change occurred gradually over time, making trends approximately linear. Next, the model is simple and interpretable. The slope provides meaningful insight and increasing or decreasing force. And last, it performs well for time-based prediction with limited features. Next is the k-means clustering or pattern discovery. K-means is used to group countries based on similarity using average forest coverage and trend or slope that we get from the linear regression. The algorithm assigns countries to clusters by minimizing the distance to cluster centroids. Why we choose k-means? Well, it's effectively groups similar patterns in data. It is simple and efficient for large datasets. It works well with numerical features like average and slope. And lastly, it helps identify meaningful categories such as improving or declining countries.
In this project, we successfully built a machine learning system that combines prediction and clustering. We trained a regression model for each country to predict future forest coverage, and we applied k-means clustering to group countries based on their characteristic. Additionally, we developed an interactive system that allows users to explore predictions, visualize trends, and view top countries in each cluster. The evaluation metrics in this section, we evaluate the performance of our model using two key metrics, mean squared error and inertia. First, the mean squared error, or MSE, is used to evaluate the regression model. It measures the average square difference between the predicted and actual forest value. In our case, the MSE is 0.33. which is very low. This indicates that the model's predictions are very close to the actual data. In other words, the regression model is highly accurate in capturing the trend of forest coverage over time. This is expected because forest changes typically occur gradually, making linear regression a suitable approach. Next, we evaluate the clustering performance using inertia. Inertia measures how close each data point to its assigned cluster centroid. A lower inertia values indicates more compact and well-defined cluster. In our model, the inertia value is 20,000. While this number may seem large, it is influenced by the scale of the data, since we are working with squared distance and multiple countries.
To validate the reliability of the model, we use k-fold cross-validation. In this approach, the dataset is divided into k subsets, where k equals 5 in our case. The model is trained on 4 subsets and tested on the remaining one, and this process is repeated multiple times so that each subset is used as a validation once. The error from each iteration are then averaged to obtain the k-fold MSC. This method is important because it evaluates the model on different portions of the data rather than relying on a single train test split. As a result, it provides a more reliable estimate of how the model performs on unseen data. In our project, the k-fold MSC is close to the training MSC, which indicates that the model generalizes well and it is not overfitting. Therefore, we can conclude that the model is both accurate and robust.
In this project, the system is designed with several user inputs and features to make the analysis interactive and easy to use. First, when the user insert one to select this feature, the user can input a country name, and the system will then provide prediction for future forest coverage, specifically for upcoming years 2024 and 2025, along with the cluster category of that country. Additionally, the user has the option to visualize the trend using a plot. Second, the user can select a cluster category, such as forest rich or improving. The system will return the top 5 countries within that cluster based on highest average forest coverage. This allows users to compare and analyze countries within the same group. Third, the system provides a features to display model performance, including MSE, inertia, and key-fold validation result. This helps users to understand how accurate and reliable the model is. This feature was selected to ensure that the system is not only predictive but also interactive and informative.
All the process will be stored in a function program individually based on the usage. First, it is the data input and pre-processing. The process begins with collecting the dataset, which contains forest coverage data for each country across multiple years. The data is then cleaned by removing unnecessary columns and handling missing values. After that, the dataset is transformed into a time series format, where each row represents a country, a year, and its forest coverage. This step ensures that the data is consistent and ready for modeling.
The second one is linear regression. Next, we apply linear regression to model the relationship between year and forest coverage for each country. The model learns a line that best fits the data, representing how forest coverage changes over time. From this model, we obtain the slope, which indicates whether the forest is increasing or decreasing. And this step is important because it allows us to capture the overall trend of each country.
Next is the feature extraction. After training the regression model, we extract two key features for each country, the average forest coverage and the slope of the regression line. The average represents the current condition of the forest, while the slope represents the rate of change. These features summarize the entire time series data into meaningful indicators that can be used for clustering.
The next one is k-means clustering. Using the inserted features, we apply k-means clustering to group countries based on similarity. The algorithm assigns each country to a cluster by minimizing the distance to the cluster center. Through iterative updates, the centers are adjusted until the cluster is stabilized. This step allows us to identify patterns, such as countries with high forest coverage or those experiencing improvement or decline.
Next is prediction. Once the model is trained, we use the regression equation to predict future forest coverage values for each country. For example, the system can estimate values for upcoming years, such as 2024 and 2025. These predictions are based on the learned trend from the historical data.
The last step is to record clustering data. Finally, after being clustered, each cluster member will be recorded in one variable for the output usage.
First, for the MSE calculation, we first use the trained regression model to predict forest values for each year. Then we compare these predicted values with the actual values from the dataset. For each data point, we calculate the difference between actual and predicted values, square the result, and sum all of the errors. Finally, we divide all the total numbers of data points to get the average error. This gives us the mean squared error, which indicates how accurate the model is. For the inertia, each country is assigned to the nearest cluster centroid based on distance. Then, we calculate this distance between each data point and its assigned centroid. These distances are squared and summed across all data points. The final value is called inertia. A lower inertia means the clusters are more compact and better formed. For the k-fold calculation, the dataset is first shuffled and divided into k equal parts. In each iteration, one part is used as validation data, while the remaining parts are used for training. The model is trained on the training set and evaluated on the validation set using MSE. This process is repeated k times so that each subset is used as the validation once. Finally, all MSE values are averaged into produce the final k-fold score. This helps ensure all the models performs consistently across different subsets of data.
For the output, it consists of four main output. First, the future prediction for forest coverage in 2024 and 2025. Second, the visualization. The third one is the top 5 countries for selected cluster. In this case, is the top 5 country for forest-rich cluster. And the last output is the performance of the model itself.
In conclusion, this project successfully applies machine learning techniques to analyze forest coverage data. Linear regression was used to predict future forest trends, while k-means clustering was used to group countries based on their characteristics. The model achieved high accuracy as indicated by the low MSE, and the clustering results were reasonably well formed based on inertia. Additionally, k-fold validation confirmed that the model performs consistently on different subsets of data, ensuring its reliability. Overall, the system not only provides accurate prediction, but also meaningful insights into global forest patterns, making it a useful tool for analysis and understanding.